Hello and welcome back, guys, to Code a Key. In this video, we're going to discuss check for prime. We are under data structure algorithm series in Python, and the second chapter, that is mathematics. Let's see checking the number for prime. Okay, so the problem itself says we are going to check the number for a prime. That is, we're going to do primality test. Okay, primality test. So what we're going to do, we're going to check for prime. It is this particular topic is used under cryptography. Okay, and what is opposite for checking for prime? It is checking for composite numbers. And do we have any kind of algorithm for checking for composite? Yes, we have. That is Miller and Rubin algorithm. And I want you to go through this algorithm for a bit. Okay, and if you can understand, because it is not compulsion, because if it is not prime, then it is going to be a composite, so we can use the same algorithm for checking composite also. Okay, so but this is a particular algorithm that you can go through for checking whether the number is composite or not. Now let us move towards prime. So primality test. What exactly prime numbers are? Prime numbers are those numbers which are which are divisible only by 1 and the number itself. Example, 7 comes only in the table of itself as well as table of 1, right? So these are the factors of 7, so they are not going to have any other factor than 1 and itself. So this is prime numbers. So what we can have, very basic and very naive algorithm for checking whether the given number is prime or not. That is going through the numbers from 1 to that number itself, right? So that means we are going to go from number 1 to that number itself, that is n plus 1, right? So we're going to use for I in range, something like that. So the range is going to be 1 to n plus 1, and we know that 1 is always going to be there and n is also going to be there in in our factors. So we can go from range 2 to n, right? So here compulsorily we're going to have two factors, right? So we're going to say if factor is 2, then yes, it is prime. And over here in this case, we're going to have factors just as 0, right? We're going to not have any factors in this. So if this is the case, then it is prime. So if you change the range, the condition also changes, right? So yes, this is a very naive algorithm for solving or checking whether the given number is prime or not. Okay, now let us optimize it, because we are going too much numbers, so many numbers, right? They go off, and we're going, if we have 100 to check, so we're going to go from 2 to 100, right? We need to decrease the range, we need to lesser the comparisons. So for that, uh, consider a situation, something like, you need to check whether the given number 100 is prime or not. Okay, consider a situation where we need to check 100 is prime or not. So for checking 100, we know that it is not prime. So now let us write the multiples of 100. Sorry, factors of 100. Something like 2, 4, 5, 10, 20, 25, and I guess 50, right? So these are all the numbers that are factors of or multiples of, yes, factors of 100. And what you can observe over here is the largest factor is 50. Okay, largest factor is 50, that is n by 2. That is what? That is n by 2, right? And this hold true for all the numbers. That is, so we are going to test all possible divisors from 2 up to n by 2, right? So we have decreased our range from 2 to n by 2. So again, we are going to have same complexity, that is big O of n, but we have decreased our comparisons and divisions, right? So now this is one of the approach, going till n by 2. Yes. Now let us see something more, something like, what are the factors? We have 2, 4, 5, 10, 20. 2, 4, 5, 10, 20, 25, and 50, right? So these are all the factors. Sorry, yes, factors of 100. What you can see is how we can write 100 from here. We can write 2 into 50, right? Similarly, 4 into 25, then 5 into what? 5 into 20, 10 into 10, 20 into 5, 25 into 4, and 50 into 2. So these are all the what? You know, multiples. We have just had hundreds. What you can observe here, what over here is that we are getting repetition. 20 and 50 is repeating, 20 and 50 is repeating. 40 and 4 and 20, 4 times 25, 25 times 4, 5 times 20, 5 times 20, and 100, 10 times 10. Okay, this is it. Okay, what you can see is these things are repeating, right? These thing is repeating until when it is not repeating. It is not repeating until 10. Okay, we're not going to have any factors repeated until root of that number. So this is going to hold true for all the numbers. Okay, all unique divisors of n uh, are numbers which is less than or equal to. Okay, it is going to be less than or equal to root n. So again, we have minimized our, you know what, uh, our comparisons from 2 to int of course we're going to consider integer of root n plus 1. Is it, you know, are you getting it? So now here we have reduced our comparison, and by that our complexity also get, improved by root n. Okay, by root n. Was that simple to understand? Repetition, it is repeating until the root nth form, and you can take any example and you're going to get the same result. Okay, hundreds is easy to interpret, so I have taken that number. Now again, let us take an example, one more, for 17. Okay, for 17, let us check primality of 17. We are going to go from 2 to root n, right? 2 to some numbers and then till root n. That is from 2 to some numbers, root 17. And I just calculated and I found that root 17 is approximately something like 4.13. Okay, something like this. So approximately 4. We're going to consider integer. So we need to go till 1, 2, 3, 4. So what I said, greater, less than, or equal to. So we're going to go through 2. We're going to go through 3 and 4. 3 and 4. We're going to divide 17 by all these three numbers, and we found that it is not divisible by any of these numbers, and we can say that it is a prime number. It is a prime number. Therefore, in root n complexity, we go of root n complexity, we have found that 17 is not a prime number by reducing, number of comparisons and calculations, right? One more improvement what you can do over here is, what you can see is, here we are checking it for 2 also and 4 also. If a number divides 4, is it going to divide, or sorry, if a number is divisible by 2, is it going to be divisible by 4 also? Or something like, for we can avoid for checking even numbers which are greater than 2. Yes, because it because if an even number can divide n, so can 2. Means if we have something 8, if that number is divisible by 8, so it is divisible by 8 2. So we will, there is no need to check for even numbers if it is divisible by 8 2, right? So we need to check for 4, because if 4 could evenly divide 17, so can 2 also divide. And we have already checked 2, that is already in the list. Okay, so we don't need to check for 4. So in this algorithm, what we can improve is, if the number is divisible by 2, we are going to of course going to stop. But if it is not divisible by 2, then the rest numbers are also not going to divide, so we can avoid 4, and so on, like 8, 10 also, right? If I'm able to clear, if I'm clear. So for checking 17 by the algorithm which we have improved, we are not going to have 4 in our list, we are just going to divide it by 2 and 3. Okay, because if it is divisible by 2, then all the rest numbers can also divide that number, evenly divide that number, right? Right. Yes. So this is one of the few optimizations that we have done. Now, before moving forward, or before coding, or let's code the solution first, right? Yes, let's code for this method, and then we will see a property of prime numbers, and then we will code using that method. Okay. So let's see. what we need to do is we need to check whether the given number is prime or not. So first of all, we're going to have a factor variable, right? So this factor variable initialized to 0. If it is 0, then we will say that yes, the given number is prime, right? So we're going to go for I in range from 2 to square root of, I have, uh, imported square root of n, okay, and we need its integer part, so integer will be added at the end, right? So this is our range that we're going to check. Now if n is divisible by I, then we will increment the factor by 1, right? Okay, so if factor's value is equals to 0, then we will say we'll return true. Okay, if it is not, then we will return false. Simple. Now in our main part, what we're going to have an if statement, something like if check primes n is true, then print something like, we use f string, the number n is prime, right? If it is true. Else we're going to have something like print again f string, the number n is not, right? No issues over here, I guess. Now let's see. Sorry, sorry. Check prime. Now let us have a number 17 first of all. Yes, 17 is a prime. Let us run it again. Let's add 100 and 17. 100 is not prime. Yes, it is. Is it clear? I guess it is. Now let's see the next method. That is what? Yes, we're going to optimize this solution basically. Okay. Now we're going to improve, and I'm going to add a property which you might know, which you might not, because this is basic mathematics, right? You need to know a few properties of prime numbers and all stuff like that. So the property is all the prime numbers which are greater than 3, all the prime numbers that are greater than 3 are of the form 6k plus 1. Okay, this is the property because all the numbers, all the integers are of the form 6k plus I plus minus I. This is the property of all the integers, sorry, plus I, plus minus, plus I, and this is plus minus 1. Okay, so all the prime numbers are of the form this, and all the integers are of the form this. So if we have to say that 2 divides some numbers, so 2 is going to divide something like 6k plus 0, 6k plus 1, 6k plus 2, and sorry, 6 plus 1, not 6 6k plus 2, 6k plus 4. So 2 divides all these numbers. Similarly, 3 divides all numbers like 6k plus 3 and stuff like that. Okay, so this is the property of integer as well as prime numbers, that whenever, if all the prime numbers which are above 3, so all the prime numbers above 3, I'll write this down, all prime numbers above 3 are of the form 6k plus minus 1. Okay, 6k plus minus 1, where what k is equals to 0, sorry, not equals to 0 but greater than 0. K is greater less than 0. Yes, k is less than 0. Okay, and the I over here, I is starting from minus 1. Okay, I is starting from minus 1, 0, 1, 2, and so on. Okay, so this is the property, k is less than 0, and all the prime numbers which are above 3 are of the form this. So a more efficient method is to test whether our number n is divisible by 2 or 3, because if it is divisible by 2, then all the even numbers are you know out of comparison, and similarly for 3, right? So first of all, we're going to check whether the given number is divisible by 2 or 3. If it is not, then we will check, and that is then we'll go through all the numbers of the form 6k plus minus 1 less than equals to root n. Okay, going to check in this range. Okay, and this particular algorithm which I'm talking about right now is 3 times faster than all the previous algorithms, or let's say 3 times faster than this root n algorithm, okay, or method. So what we're going to do, what we're going to do, okay, one thing I like to, in this program, one base condition is like, what if user has one as an, oops, I'm really very sorry because I'm just getting off topic, or you know I forgot to tell you this. One is neither prime nor composite, right? So we need to add the condition over here, something like if n is equals to 0, sorry, 1. So we're going to print something like is not prime, right? Or don't let us return what? Return false, right? Because it is not prime. Okay, so let's check this. I'm really sorry for that. Okay, it is not prime. Okay, let's move forward. So where was I? Yes, this is it. So now let us code, right? The first thing that we're going to do is, for this algorithm, is we're going to check whether our number is divisible by 2 or 3. If it is not divisible, then we're going to go to the second step, that is, we're going to go through all the numbers in this range. And yes, I'm going to write the program first, and then I will be explaining you by dry running that particular program, and then you will be able to understand it very easily, right? So let's go to the editor. Now this is a program for, checking prime, and what we have, we are checking whether the given number is, in between the number between the range. So n is less than equals to 3, and we are checking the first step, that is, the number is the number divisible by 2 or 3. Okay, if it is, then that is not a prime. And then this is the second step, that is checking the number between 6k plus minus I till root n, right? That was our protocol. Now let us, before running it, let me explain you this, right? Because I haven't explained you why I have taken all this thing. Let us dry run this program for n's value 17. Okay, let us write it. I have taken the screenshot of the program so that, it will be easy for me to explain you with help of this. So n is equals to 17 I have taken. Okay, so now if n is 17, the first condition is, useless. The second condition is also, it is not divisible by, it is not divisible by 2, it's not divisible by 3, not divisible, so false. Now what we have over here is, we have I, so I is equals to 5. Okay, now we went into while loop, that is I is square, that is 25 square is 25. Okay, so 5 square 25 must be less than or equal to, must be less than or equals to 17. Oh, the condition is false, it is not going to go inside the loop. And so uh, it is true that the number is prime, right? Now let us try for another number, something like, you know that number must not be multiple of 2, must not be multiple of 3. Let us take, multiple of 7 only, something like 49. Okay, for 49, let's check for 49, because it is not divisible by 2, so this is not going to happen. Neither it is divisible by 3, right? And this is also not the condition. So now again, i's value is 5. Okay, and I square, that is 25, is less than or equals to the number 49. Yes, the condition is true. It went inside the loop, right? So now if that number 49, I is starting from 5, 49 is divisible by 5, is it divisible by 5? No, it is not. So this condition becomes false. It is an or statement, right? Either one must be true. Okay, and if so we have 49 I plus 2 modulo something like 7, right? 5 plus 2 7. Is it true? Yes, it is true. So answer is false. In the first iteration only we got, so false. That means the number is not prime, right? Now let us run what we have what probability test, and let us check for something like 200. Is it prime? Another prime number. 17. Is it prime? Oh, sorry. 70. Is it prime? Right. So this was very basic thing, right? Not basic, but we have thought too much into this, right? We went from checking. We try to minimize our comparisons and operations till n, then n by 2, then root n, then using the property of prime numbers, that is 6n plus minus 1, and writing the programs. You can get the code for this in the link below, that is the GitHub link below. If you want to find uh, some more tests that works, but are not proven, that I haven't discussed, you can check that out in the link below, the Wikipedia link from where the content has been taken for this video. Okay. Those type of theorems or methods whose proof is that is unproven, that is but has some property, is called as hysterics tests, and those tests are in the link below, that is Wikipedia link below. And there are more methods, that is probabilistic test, and more tests are there which you can check for checking prime ones. Okay, but they might be efficient, they might not be efficient, but we have discussed about one of the efficient method, that is the property of prime numbers, right? And we have tried to discuss, we have tried to minimize as much as comparisons as possible, right? So this was good video where we have discussed prime numbers. We have checked if the given number is prime using you know quite few methods. So in the next video we're going to have the method of we're going to see we're going to calculate the prime factors of the given numbers. So this is it for this video. Thank you for watching till the end. Do share it with your friends, like, okay, comment if you have any doubt. If you didn't understand the code, you can get the code in the GitHub link, okay, below. And yes, this is it. Yes, you can check out the previous video over here. Do subscribe, and thank you.